Hi everyone. Today we are going to study the link state routing protocol, which is another dynamic routing protocol. So the link state routing is simple and can be stated in 5 parts. First of all, the first step is to discover all its neighbors and learn their network addresses. That means this protocol first of all finds out the neighboring routers and then finds out their network addresses. Then the second step says measure the delay or cost to each of its neighbors. Now once all the neighbors and their addresses have been found, the next step is to find out the delay to reach or the cost to reach to every other neighboring router from that particular router. Then the third step says construct a packet telling all it has just learned, right? Now whatever this router has learned about all of who all its neighboring routers are, what are their network addresses, what is the delay or cost to reach to each of those neighbors, all that information that has been learned is constructed as a packet which tells all the information the router has just learned in the first 2 steps. Then the fourth step says send this packet to all other routers. Once this information is gathered in the form of a packet, it is sent to all other routers. After that, compute the fifth and the last step says compute the shortest path to every other router. The last step is to find out the shortest path from one particular router to every other router. Now in effect, the complete topology and delays are experimentally measured and distributed to every router. So the complete topology of the subnet and all the delays to reach from one particular router to every other router in this process are experimentally measured and then they are distributed. The results are distributed to every other router. Then Dijkstra's algorithm can be, after these 5 steps are complete, Dijkstra's algorithm can be run to find what the shortest path to every other router. Because what does the fifth and the last step says? After everything has been done, compute the shortest path to every other router. So the best possible algorithm to find the shortest path here is the Dijkstra's algorithm. So to find the shortest path from one router to every other router, the Dijkstra's algorithm is run and then the shortest path is found to every other router. Now we will elaborate all these 5 steps. Now the first step says learn about all your neighbors and find out who all your neighbors are. This we are talking about the routers, that is one router finds out all its neighboring routers. So when a router is booted, right? A router is booted, its first task is to learn who its neighbors are. The first thing that is done after the router is booted is to learn about all its neighbors. It accomplished this task by sending a special hello packet on each point-to-point line. How does the router learn about all its neighbors? It sends a special packet which is known as the hello packet to each and hello packet on each point-to-point line. The routers on the other end is expected to send back a reply telling who it is. So when the routers on the other end receive the hello packet, they are expected to send back a reply in which they tell who they are. Next, these names must be globally unique. Now whatever the names of the routers are, they must be globally unique. That means no other router must exist with the same name in the subnet. Because when a distant router later hears that these routers are all connected to, say, router F, it is essential that it can determine whether all 3 mean the same F. So that means if it gets to know that other routers are also connected to a router named F and it is also connected to a router named F, so it must be sure of the fact that this F is the same router to which it is connected and not some other router which other routers are talking of. So that means the names must be globally unique. If F has been assigned as a name to one router, it cannot be assigned as a name to any other router in the subnet. Hence they must be globally unique for the simple reason that one router can determine whether all the 3 are talking about the same F router if they are talking of that particular router. Now, when two or more routers are connected by a LAN, the situation is slightly more complicated. So that means when you are connected by some wires by a LAN, the situation gets complicated. How? Now if you see, look at figure A below. This is the figure A below, wherein you can see that 9 routers are connected by a LAN. We have 9 routers over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So from A to Y, there are total how many routers? There are 9 routers. And how are they all connected? They are connected through a LAN, that is a local area network. Now there is a LAN to which all the 3 routers, we are here particularly talking about these 3 routers A, C and F. So the figure below, as you saw, illustrates that there is a LAN to which all the 3 routers, which 3 routers A, C and F are connected. Now each of these routers are connected to one or more additional routers. A, C and F, as you can see, are connected to this LAN, and then again these 3 routers are again connected to some other routers. For example, router A is connected to router B, then router C is connected to router D and router E. Similarly, router F is connected to router G and router I. So another way to model the LAN is to consider it as a node itself. That means you consider the LAN as a node itself rather than as a separate wiring system, as shown in figure B below. So here you can see that this particular node represents the LAN. Like here in figure A, this was complete wiring system. This is the LAN. This line is the LAN, but in figure B we have modified this thing. That means we consider the LAN as a node itself, and now to this node routers A, C and F are connected, which in turn are connected to routers B, D, E, G and I. Now here a new artificial node N has been introduced. This is the artificial node that we are talking of. This LAN is represented as a node over here. Now the same LAN which is represented as a wire or a link in the diagram A, as you can see, is represented as a new node over here, to which obviously A, C and F are connected. That I have already told you, that this LAN is now represented as a node to which routers A, C and F are connected. Now the fact that it is possible to go from A to C on the LAN is represented by the path A and C here. If you want to go from router A to C, then you can go via the node N, which is basically nothing but the LAN represented as node N. So if you want to go from A to C, the path is A, N, C. That means from A to C, from router A to C, you can go via node N. So this is how it is represented here, that the path is A, N, C. Okay, so next step is measuring the delay or cost to each of its neighbors. Now we are done with finding the neighbors of every router. Next step is to find the delay or cost to reach to every other router from that particular router. Now each router must know or at least have a reasonable estimate of the delay of each of its neighbor. It's quite obvious that a router must be aware of the delay, or at least must, if it does not have an exact estimate, it must have a rough or reasonable estimate of what is the cost or delay of to reach the neighboring routers. Now the most direct way to determine this is this delay. How do you determine this delay? The most direct way to determine this delay is to send over the line a special echo packet. Just like to know about your neighboring routers, you send a special hello packet. Similarly, to find out the delay of to reach to every neighboring router, a special packet known as an echo packet is sent, that the other side is required to send back immediately. So when the neighboring or the other routers receive this echo packet, they are expected to send back that echo packet immediately. Now by measuring the round trip time, the round trip time is the time that is taken, that is measured from transferring a particular packet from the sender to the receiver and then then it is returned back from this receiver to the sender. So that is known as the round trip time. That means from the sender to receiver, from the source to destination, and then again from the destination back to the source. This entire time is known as the round trip time. So by measuring the round trip time, that is the time from which the echo packet was sent from the router to every other neighboring router, and the time till the time it came back from the neighboring routers to the router which had sent the echo packet, that is the round trip time. And this is measured and then it is divided by 2. The sending router can get a reasonable estimate of the delay, right? So for example, if this is the source router sends the packet to the destination router, so if I assume that 1 second's time is taken to send the echo packet from the source to destination, and then the destination router is expected to send back this echo packet to the source. So if 1 second time is taken from sending the packet from source to destination, the echo packet from source router to destination packet, and then again 1 second time is taken in transmitting that echo packet back again to the source, that means total round trip time is 1 plus 1, which is equals to 2 seconds. So you divide 2 by 2. Basically you divide the round trip time by 2. So here if the round trip time is 2 seconds, you divide 2 by 2, and then you get that this means 1 second is a reasonable estimate of the delay that will be from this particular router to this particular neighboring router. The third step says build link state packets. What do you mean by building link state packets? That means construct a packet telling all it has just learned. As we know in the third step, whatever the router has learned about its neighboring routers, be from who its neighboring routers are, or from their network addresses, or from the cost or delay to reach those neighboring routers, every such information is packed in a packet. So you have to basically construct a packet telling all about that router has just learned, and constructing such packet is known as building link state packets. So how are these link state packets constructed? Once the information needed for the exchange has been collected, you need some information to exchange it with other routers. So once all this information has been collected, what is the next step for each router? Each router is expected to build a packet containing all the data about all the information it has learned so far in these 2 steps. Now the packet starts with the identity of the sender. Obviously you need to have the identity of who the sender is. So these packets first of all contain the identity of that particular router for which the packet is being constructed, which is the sender, followed by a sequence number. What is the sequence number of that router? And then what is the age of that router, and a list of neighbors. So what information does this packet have? This packet has the identity of the sender, then it has the sequence number of the router, then it has the age of the router, and the list of all the neighbors of that particular router. So this is all the information that is contained in a link state packet. For each neighbor, the delay to that neighbor is given, right? So in that particular router's link state information, the delay to all the neighboring routers of that particular router is also given. As an example subnet, if I can show you, this is an example subnet, right? So delays are shown as labels. Whatever labels you can see here, like 3, 2, 4, these are the delays. Corresponding link state packets for all 6 routers is shown below, right? So the link state packets for all the routers are here. Like this is router A, B, C, D, E, F. The delays or cost from one router to another is shown in the form of these labels, which is 1, 2, 3, 4, 5, 6, 7. And the link state packets for all these routers, whether it is router A, router B, the link state packets for all these routers are shown here. So if you can see, The link state packet for router A is here. The sequence number would be provided for that particular router. The age of that particular router would be provided. Then which two routers are the neighboring routers of this router A? Neighboring routers means which are directly connected to that particular router. So if I see here, router B and E are the neighboring routers of router A. So the distance or the delay or the cost to reach from router A to router B, which is 4, is given here, which is labeled here in this diagram. And the cost to reach from router A to router E, which is 5, is also given here. Similarly, you can see the link state packet for router B. So the sequence number of the routers B would be provided, the age of router B would be provided, and then which all routers are the neighboring routers of router B? C, A and F. So the delay or cost to reach from router B to router A, which is 4, is provided. The delay or cost to reach from router B to router C, which is 2, is provided. The delay or cost to reach from router B to router F, which is 6, is provided here, and so on for all other packets. So this is how the link state packets are constructed. Next, or the fourth step says distribute the link state packets. That means once those link state packets are constructed, the next task is to distribute those packets so that other neighboring routers also know the information about their neighbors. So the fundamental idea is to use flooding. Now how do you distribute this packet? That means basically you have to broadcast the packets because you want this information not to be sent just to a single destination router but to multiple destination routers. So what is the best approach to do that? Of course, we know when we have to broadcast data, we can use the flooding routing algorithm. So the best or the fundamental idea to do this is use flooding to distribute the link state packets. To keep the flood in check, right? So that no packet is sent more than once. Each packet contains a sequence number. Now each packet has its sequence number that is incremented for each new packet sent. So every time a new packet is sent, this sequence number is incremented, and routers keep track of all the source routers, sequence numbers and pairs they see. That is the destination to source to destination pairs that they see. So when a new link state packet comes in, it is checked against the list of packets already seen, right? The list of packets which have already been received or seen, that new link state packet is checked against them. If it is new, it is forwarded on all lines, obviously except the one it arrived on. You cannot send it back to the same line where it arrived on. So if a new packet is received, it is forwarded on all lines. That means it is forwarded to all the routers except to the one from which it arrived. If it is a duplicate packet, it is obviously discarded because we do not need duplicate packets, and this is how we control flooding. If a packet with a sequence number lower than the highest one seen so far arrives, it is rejected. Obviously, because every time a new packet arrives, this sequence number is incremented. So that means a new packet that you will receive will be of the sequence number higher than the previous sequence number. So obviously then it is a new packet. But if it has a sequence number lower than the recent sequence number of the recent packet, that means it is being repeated. Obviously a new packet will not have a sequence number lower than the present sequence number of the present packet. So that means if the sequence number of a packet that arrives is lower than the highest one seen so far, obviously it is rejected for the simple reason that it is duplicate or it is obsolete, and since the router has more recent data, so it is not required anymore. Now the fifth and the last step is to compute new routes, right? Every time the cost or delay to a particular route changes, we have to keep updating those routes. So that means we have to compute new routes so that we can find the best available shortest path. So that means you have to compute the shortest path to every other router, from one particular router to every other neighboring router. Once a router has accumulated a full set of link state packets, right? So that means a router has accumulated a full set of link state packets. That means it has received link state packets from every other router in the subnet. It can construct the entire subnet. Of course, if it has the link state packets from every other router in the subnet, that means it has the complete information about the entire subnet. Hence, it can construct the entire subnet graph, right? In that case, it is very easy to construct the entire subnet graph because every link is represented in the link state packet. because if you look at these link state packets and if you don't look at the graph, from these link state packets you can directly find out which router is directly connected to which other router and what is the cost to reach from that particular router to those neighboring routers. Like if I do not have this graph of the subnet, I can clearly say A is directly connected to B and E, and the cost to reach from A to B is 4 and the cost to reach from A to E is 5. Similarly, router B is directly connected to A, C and F, and the cost to reach from router B to A is 4, from router C to B to C is 2, and from router B to F is 6. So this way obviously it is very easy for me to construct a graph of the subnet, because with the help of these link state packets I have the complete information of the subnet now, so I can easily construct a graph of the subnet, right? So once, that is why they say that once a router has accumulated a full set of link state packets, it can construct the entire subnet graph, because every link is represented. Then every link is in fact represented twice, because if A is connected to B, then obviously B is also connected to A. So that means every link is represented twice, once for each direction. That is from A to B also, and then from B to A also. Link is same. If router A is connected to router B, that means in the link state packet of router A also this information will be represented, and in the link state of router B also this information will be represented. That means every link is represented twice, one for the link state protocol of router A and second time for the link state protocol of router B. So this way every link is represented twice, once for each direction, once from A to B and another time for B to A. So the two values can be averaged, right? The two values, that means the cost of these two values can be averaged for A to B and back from B to A, and then you can find out an average of this cost, or you can use these values separately, once for A to B and then another from B to A. Now you have to find out the Dijkstra's algorithm to find out the shortest path from one router to every other router. So that means Dijkstra's algorithm can be run locally to construct the shortest path to all possible destinations. And the result of this algorithm can be installed in the routing tables, because the routing tables need to be updated regarding the shortest path from that particular router to every other neighboring router or every other router in that subnet, even if it is not a neighboring router. So the results have to be installed in where? Routing tables, because this is where the routers take their information from. And then normal operations are resumed. For a subnet with n routers, that means if there are n routers in a subnet, each of which has how many neighbors? K neighbors. So that means a subnet which has n routers and k neighbors, how much memory is required to store the input data? It is proportional to k times n. That means as much memory as equal to k times n, which is equal to the number of neighbors and the number of routers multiplied together. For larger subnets, if the memory for n routers and k neighbors is k times n, then obviously for larger subnets this can be a problem, because the memory requirement would be large enough in such cases. Also, the computation time can be an issue, because when there are large number of routers, large number of neighbors, the computation time will also stretch. But nevertheless, in many practical situations, link state routing works well as long as the subnet size is limited. So this is all about the link state routing protocol.